Hello, algebra students. This is going to be our lesson video on using function notation to describe rules. You'd notice right here up at the top that this is part 1. So we are starting this conversation today and then going to continue it tomorrow. The focus of this particular lesson is right here. We are going to be looking at some rules that describe functions and writing those rules as well. The focus tomorrow is going to be on this, but also bringing in some of our graphs that we've been using. For our warm-up for this lesson, it's going to be about inputs and outputs. The question we are looking at tells us that the function takes any input and cubes it to generate the output. Meaning you put something into the function, it cubes whatever you put in, and then it gives you an output. That word cubed is something we're going to need to know in order to do this problem. Remember, cubing something means that the exponent is a 3. So for example, if I write this, that means 4 cubed. So it's describing an exponent. The function is using that exponent of 3. For the first part, our goal is to find the output when the input is 0, when the input is 1, when it's 3, and then if it's an x. Go ahead, pause the video, because that's going to be the best way for you to get some practice and see where you're at. Pause the video and try this first question here, and then press play once you've got some answers. Well, we know this function cubes whatever the input is. So if my input is 0, and I'll keep track of these, if my input is 0, to get my output, I just need to cube 0. So I would do 0 cubed. Remember, cubing something means you're multiplying it by itself 3 times. So my output would still be a 0. And we could do this for the other ones. If my input is the number 1, my output would be 1 times 1 times 1, which also happens to be 1. If you're thinking 3, you're thinking 1 plus 1 plus 1, not 1 times 1 times 1. There's one last one. That is if our input is the number 3. If you didn't get these two earlier, go ahead and pause the video to try an input of 3. If our input is 3, our output is going to be 3 cubed. So that would be 3 times 3 times 3. Well, I know 3 times 3 is 9, and then 9 times 3 gives us the output of 27. So I've got 3 pairs of input and outputs. The last one here is if our input is x. Well, if our input is x, I can't actually do any of the math because there's no number here. But I can describe what the output would be, because whatever we put as our input, I just need to cube it. So if my input is x, my output would be x cubed. And this is the direction we're going today. When we say we're looking at some rules that describe functions and writing them, the rule here is this idea of cubing whatever you put into the function, and writing that rule is going to look like this right here. Instead of all these specific examples, we can make a general description of our function by just saying the function is x cubed. Now, the second part of this question says write the input-output relationship using function notation and naming the function g. Last week and in earlier lessons in this unit, we've talked about function notation. We said when you're writing function notation, you start off with the name of the function. And they've told us the name of the function is g. And g goes here. And then after the name of the function, in the parentheses, is our input. Here, we are talking about an input of x. So I'll put x there. And then what comes after that is just your output. We said earlier when the input is x, the output is x cubed. So I can write this relationship with function notation by saying g of x equals x cubed. I'm going to put some notes with this just as a reminder. If it's been a minute since you watched that function notation video, or if you missed class when we talked about function notations, I would definitely put this down in your notes. This part here is always the name of the function. So they told us this function is going to be named g. This part right here, what's inside those parentheses, is your input. And then this part right here is describing our output. So like we had said earlier, if you put x into this function, out comes x cubed. This right here is going to be one of the focuses for what we're doing today. It's looking at these functions and these relationships and being able to describe the rule for that function using function notation. So writing more things like this today. Now, this was our first example. Our first one was about the situation where the function cubes whatever you put into it. The next part of this is going to give us more examples of this function notation and how it's being used to describe rules. So for this next part here, we are going to look at 4 functions, as the name of the activity suggests. And our first goal is going to be matching these 4 function notations with a description of what that function is doing. So the directions say, here are descriptions and equations that represent the 4 functions. On the left, we've got all the function notation, and on the right, we've got those descriptions. Our first question tells us to match each equation with a verbal description that represents the same function and record your results. The challenge here is all of these are similar, right? We've got 3's, 7's, and x's in each of them. So we really want to pay attention to the wording of that function. Go ahead, pause the video to make sure you're getting that practice in and see which ones you can go ahead and match up on your own, and then press play to come back and hear how you did. Go ahead and do that now. All right. So as we're looking at these 4 functions, there are 2 pairs of similar functions, I would argue. Both of these first 2 involve multiplication, and these last 2 involve division. The difference has to do with how much of the function is being multiplied or divided. So right away, as you're reading through these 4 descriptions, all of them are going to mention subtracting that 7. But as I'm comparing them, I see this one here is talking about division. This one is multiplication. This one also mentions multiplication. And this one also mentions division. These first 2 here are my 2 that have multiplication. I know this because 3x means 3 times x, and that 3 in front of those parentheses also means multiplication. So I know function f and function g are going to have to match up with b or c. It's just a matter of which one goes with which. When I read through B, it says to get the output, subtract 7 from the input, then multiply the result by 3. And when I read C, it says to get the output, multiply the input by 3, then subtract 7 from the result. So the difference between B and C is the order that math is happening. The first one says we want to subtract 7 first, then multiply that result by 3. When I'm comparing these 2, the one where we would be subtracting 7 from the input first would be g of x. See that x minus 7 parentheses? That's telling me I would do that x minus 7 first, and then whatever that result is, multiply that by 3. Therefore, g of x, I'm going to match up to b. Similarly then, paying attention to the order, The other multiplication one must go with function f. This one here says you're multiplying the input by 3 first. That's our 3x. And then afterwards, we're subtracting 7 from the result. These last two here are going to be similar. So if you weren't able to match up any earlier, go ahead, pause the video again, and see if you can figure out h and k. Or if you do have them matched up, just verify that you've got them matched up correctly based on this first part. Again, it's all about the order here. When I'm looking at function h, that division would happen first, and then the subtraction would be happening second. When I look at function k, the subtraction would be happening first, and then I would be dividing my result by 3. So based on that, k of x is going to go with a, because a says subtract 7 from the input, then divide the result by 3. And then one last one, h of x would be down here with d, because we're dividing the input by 3 first. That's our x divided by 3, and then subtracting 7 second. So that is how our 4 functions match up with the descriptions. Now, we don't use these descriptions a lot of the time, but we do definitely need to know what these 4 functions are describing, especially because our end goal here is we want to be able to write things like this ourselves. The next set of questions are still about these 4 functions, but have a little more to do with how we find inputs and outputs for them. So jumping down to number 2, number 2 says for one of the functions, when the input is 6, the output is -3. Which is that function? Function f, g, h, or k? And then, like many of our questions, explain how you know. There's not really a strategy to this. It's just a matter of guess and check. So checking each of these functions to see which one would give you an output of -3 if the input is 6. This is where we get to use some algebra skills and substitution. So for our first one, if I want to see if function f is our correct answer, I want to figure out what function f is when the input is 6. So I'm going to put a 6 there to show that my input is a 6. When I go to evaluate what function f is going to be, it's more substitution. So anywhere I see an input, which here is the letter x, I'm going to be putting the number 6. So that means if our equation says f of x equals 3x minus 7, I'm putting a 6 here for my input, and then doing 3 times 6 minus 7. If we do some more math with that, 3 times 6 is 18, and 18 minus 7 is the number 11. Great math right there, but that's not an output of -3. So I know it's not function f. There's 3 more functions for us to try. Go ahead and pause the video now. See if you can figure out which one of these is going to give us that output of -3. All right. Like I said, there's not a ton of strategy here. It's just going down the list until you find which one gives you the output of -3. Hopefully you didn't have to try too long, because when you get to that next one, G, you're going to see that when we make our input 6, it's going to be 3 times 6 minus 7. Here, I got to do that subtraction first because it's in parentheses. 6 minus 7 gives us -1, and 3 times -1 is -3. So for number 2, which function is it? It is function g. For that explain piece, explain how you know, I would just say for function g, I made my input 6, and when I did that, we get 3 times 6 minus 7, which equals 3 times -1, which equals -3. For that explain piece, I would just say exactly this. This right here is the proof that the output is -3. For the other question here, which function value, f of x, g of x, h of x, or k of x, is going to be the greatest when the input is 0? What about when the input is 10? This is going to be similar work to what we did above. It's evaluating functions when we know what the input is. Go ahead and try number 3 now. We're looking at number 3 first for which of those functions is going to be the greatest when the input is 0. If we make f of x the input 0 for that, so f of 0, that would give you an output of -7. G of 0 would be a -21. H of 0 would be a -7. And then I'm running out of room. K of 0 would be -7/3. Looking through these, there's not a lot that's really a large number since they're all negative. Remember, when you're comparing negative numbers, it helps to think about a number line. The largest one is going to be the one closest to 0, which would be our K of 0. We could do a similar thing when the input is 10. So for 10, f of 10, remember I'm just substituting these numbers into these functions. So for f of 10, I'm doing 3 times 10, which is 30, minus 7. So f of 10 would be the number 23. G of 10 would be the number 9. H of 10 would be 10/3 minus 7. So that would be -11/3. Main thing is it's negative, so it's not going to be our largest one. And then K of 10 would be the number 1. Looking through these, the one with the greatest output would be function f when we're talking about the input being 10. The purpose of these here is just to practice evaluating these functions when we know the input. And the key here, I think, is just a lot of substitution. I'm going to write that word down. It's a lot of substitution. Substitution. Just this idea that we're replacing our input, our x, with whatever number that's given to us. So that's the first part of this lesson. The focus of this first part, remember, was this idea of being able to use function notation to help us describe functions. And like right here is this matching activity where we were matching the descriptions of functions with that function notation. And then the second part here was evaluating these functions. And we said evaluating is just a lot of substitution. There's one last part to this lesson, and it has to do with us actually coming up with this function notation ourselves. Notice so far with these, all of these equations were already given to us. We didn't have to write that function ourselves. We just had to understand what it meant. The second part of this is going to be us looking at situations. So our situations today are going to be about area and perimeter, and us actually coming up with that function and using function notation ourselves. So the first one here is going to be all about area. Looking at the first part of this problem, we are told that a square has a side length a square that has a side length of 9 centimeters has an area of 81 centimeters squared. Let's pause there. Why is that? What do we remember about area? Well, area we've talked about with like squares and rectangles. You're just multiplying your two sides, your length times your width. And so it tells us in the next sentence, the relationship between the side length and the area of the square is a function. It's this idea of we're looking at the side length of a shape. So for example, if it's a square, that's 9 by 9, and squaring it to get to that area. That 9 times 9, or 9 squared, gives us the area of that square. So this right here is just an example. For example, if a side length of a square is 9 centimeters, the area is 81. Let's go ahead and fill out this table over here with more examples of area. In number 1, it says complete the table with the area for each of the given side lengths. And then the second part of this is writing that function rule. For now, similar to what we did up here when the side length is 9, I'm going to have you go ahead, pause the video in a moment, and complete these first 4 rows. So if the side length is 1 centimeter, what's the area? If the side length is 2 centimeters, what's the area? And it helps here to keep track of what math you're doing. So instead of just putting an answer, kind of like what we did up here with the 9s, keep track of what math you had to do to get to that answer as well. Go ahead, pause the video, and come back when you've got those first 4 rows done. All right. Well, as we had set up here, it's this idea of you are squaring the side length or multiplying it by itself. So for all of these other ones in our table, it's going to be the same math. I have to do 1 times 1 or 1 squared to get an area of 1. I have to do 2 times 2 or 2 squared to get that area of 4 centimeters squared. 4 squared or 4 times 4 to get the area when the side length is 4. And then the last one, 6 squared, to get an area of 36 centimeters squared. Each time to find the area, all we're doing is taking that side length and squaring it. The purpose of this table here is to give us some examples so that we can practice thinking through what math we would need to do in order to get to this end goal of actually writing the function ourselves. So when it comes to writing the function notation for this rule, this idea of finding area, seeing all the math we've been doing this whole time can be really helpful. I can make the observation each time I'm just taking whatever that side length is and squaring it. I'm using that exponent of 2 to find the answer. So that means if I give you a side length of s, the only difference is I don't have a number, but the math I need to do is the same thing. I'm taking my side length, and whatever I'm giving you here in that first column, we're just squaring it. So I'm adding that exponent 2. This right here describes all of the math we did in those above rows. To find our area, I'm taking our side length and squaring it. This right here is what I need in order to help me use function notation to describe this. We are told here that the function is named a. That is going to be important because we said earlier the name of the function is what comes first. So I'm going to start off by writing this is function a. Then in parentheses after the name of the function is what we're calling our input. Here we're calling our input s. So I can say a of s. After that, when I go to write my equation, is our output. Our output is what we've got right here. A of s equals s squared. I'm going to just put in words what this means here. Similar to what we were doing up here with that verbal description of the function. This is saying to find the area, because that's what we're finding here in this function, to find the area of a square with side. I think I need to make this smaller. Hold on. There we go. To find the area of a square with side length s. Oh my gosh. Square the side length, or square s. That right there is what that function notation is telling us. Now, when we get down to number 2, it's asking us a specific question using function notation now. So we've got our function using function notation. What does a of 2 represent in this situation then? And what would its value be? Let's start off with that first question because there's 2 questions here. What does a of 2 represent in this situation? Well, when I'm looking at a of 2, I'm noticing 2 is in the parentheses. That tells me that 2 is our input, which here means it's the side length we're talking about. So this right here is talking about if the side length of our square is 2 centimeters. A of 2 then is going to represent the area when our side length is 2 centimeters. Let me write that down. A of 2 represents the area of the square when the side length is 2 centimeters. The second part, I'm not British. Centimeters is about right. The second part of our question is, what is the value? So A of 2 represents the area of the square when the side length is 2 centimeters. What is the area? Well, we've already done that in our table. I see up here when the side length is 2 centimeters, the area is 4. Therefore, I can say A of 2 equals 4. And I'm going to put a bonus what that means, which means the area is 4 centimeters. I'm going to use that to do squared. So the area is 4 square centimeters, like it's written up here. I could write all of these different rows in our table using function notation similar to this and similar to A of 2 equals 4. For example, that fourth row with the 6, I could say A of 6 equals 36. That just means when our side length is 6 centimeters, the area is 36 square centimeters. So a good chance for us to practice using function notation again. There is one last part to this, and that's this idea of looking on a graph what this function would look like. Remember, we said the focus tomorrow is really bringing in more graphs to our conversation about functions and function notation. This is going to help get us ready for tomorrow's conversation. If I wanted to sketch a graph of this function, I can use this table to help me do so, because there's already some pairs of numbers we know related to like the side length of a square and then what the area would be. The first pair of numbers I've got in my table, I could go ahead and plot that as a point on our graph. That first pair of numbers means if the side length of our square is 1 centimeter, the area is 1 square centimeter. I could show that on our graph by saying if the side length is 1, the area is 1. Now, when I'm looking at my graph, I see that y-axis is counting up by 10. So be careful. I want to do 1, 1. So that's going to be pretty low right there. That blue point, I'm just going to write over here, is at 1, 1. I've got a second row in our table that says side length of 2, area of 4. So I could go side length of 2, area of 4. That's going to be right there, close to that middle point. So that's 2, 4. And I can keep going. Side length of 3 centimeters isn't in our table, but we know how to figure it out because we've got our function notation here. If I make my input 3, my area would be 3 squared, which is 9. So I could go ahead and I could mark 3, 9 on our graph. So still under that 10. And then keep going. So when our input is 4, this one I do have in our table, the output is 16. Meaning when our side length is 4, the area is 16. So that's going to be like halfway between the 10 and the 20. So maybe like right there. And what's the color I haven't used? Here we go. We've got 5 down here. If our input is 5, the output would be 5 squared. So that's 25. So I could do 5 centimeters and then up to 25. That's definitely halfway between 20 and 30. So let me try getting that halfway point. And then for these last couple, I'll do them quickly. 6 is already in our table. We've got 636, so that would be about here. 7, we don't. 7 squared is 49, so that's up here. And then 8 squared would be 64, and that's off of our graph. As you're looking at this graph here, we've got these points. And if I were to connect those points, you can see it's making a type of shape. It's kind of curving up like that. I'm allowed to connect all of these because, yes, we can have side lengths of whole numbers like 1, 2, 3, but you could also have a side length of 0.5 centimeter or 2.5 centimeters. So there's also going to be all those points in between these ones that we've marked. Now, as we're looking at this graph here, in an earlier unit, we talked about linear equations. What do you all think? Is this a linear graph? Would this be a graph of a linear equation? The big difference here for this graph compared to other graphs we've seen is that this graph is curved. Linear equations, they get that name linear from line. Linear equations were straight lines. So as I'm looking at this, this is not a linear function. This is something else. So a preview of what we're going to be talking about in later units in this class is going to be functions that look like this. These aren't linear functions. They're a different type of function that is in your future. So this one right here, this is an example of us describing this relationship about area using function notation. We can see how a table is a great tool to use if you're having trouble coming up with that function notation and describing that function rule. We were able to keep track of that math we were doing here to ultimately come up with s squared is that rule that we're trying to describe. And then we also got to see what the graph looks like based on that table as well. I did this one here about area. There's one more in our lesson. This one is going to be related to what we know about perimeter. I'm going to go ahead and get us started together, I think, and then I'm going to have you finish this one up. So to get us started, this one here, the goal is still the same. The goal is looking at the situation. Can we use function notation to describe what's going on? And in the second one, we are talking about a roll of paper that is 3 feet wide, but it can be cut to any length. I have a picture. I don't know what happened to my picture though, but to give you an idea, we've got a roll of paper. Here's my roll of paper. And you can stretch that roll of paper out to any length and cut it down. What we do know about that paper is that it is 3 feet wide. So the width of our paper is 3 feet. The length, though, can change because you can cut it wherever you want. So what we are trying to figure out here is the side length of that paper, so how long you decide to cut it at, and then the perimeter. So for example, if the side length is 1 foot, if I decide to cut that paper 1 foot long, what would the perimeter of that paper be? Well, perimeter, remember, tells us the distance around something. So to find that distance, we're using addition. I would want to add my 3 plus my 1, but don't forget there's 2 other sides. So plus another 3 plus another 1. When you're filling out this table, just like last time, we want to keep track of that math we're doing. So here I did a 3 plus a 3 plus a 1 plus a 1, and that gives us 8. The perimeter would be 8 feet. Now that 1 is going to change because that first row we were given a side length of 1, but notice in these next 3 we were given a different side length. So this is where you're going to take over. Go ahead, pause the video now, and see if you can find the perimeter of these next 3 given these different side lengths. Go ahead, do that now. All right. So if I keep using this picture here, the only thing that's changing as we change these side lengths is this other number we're adding in. So for a side length of 2, to find my perimeter, I'm still adding my 3 plus 3. But now I would be adding 2 plus 2. So 3 plus 3 plus 2 plus 2. That's going to end up giving me a perimeter of 10 feet. Similarly, if we decide to cut that paper with a length of 6.3 feet, that means this side here is 6.3 feet and this side here is 6.3 feet. Well, we would still have to add 3 plus 3, but now for our other two sides, we're adding 6.3 plus 6.3. That would end up adding up. Oh no, I don't have enough room. That would end up adding up to 18.6 for our perimeter. So for this next one, 11, I don't even need my picture anymore because I know each time I start off with my 3 plus 3 for those two, the two widths, but then I would be adding in my side length twice. And then when I go to add that up, that's going to give me a total of 28 feet. So we said we're keeping track of all this math to help us when it comes to the last part, which is just describing this function in general with no specific side length, instead just using L to represent our side length. If you've been keeping track of the math you're doing, you're going to notice there's something that's consistent each time and something that's changing each time. As I look at my math here, every single time I started off with that 3 plus 3, because no matter what the side length is, if I need to find perimeter, I have to add that width of 3 twice. So when it comes to this general rule of what I need to do, I don't care what number you put as that side length, I'm still going to start off with a 3 plus 3. What is changing is what comes after. For this first one, I ended up adding 1 plus 1 because our side length was 1. For the next one, I added 2 plus 2 because our side length was 2. When we did that last one, I ended up having to add 11 plus 11 because the side length is 11. So to finish up this one here, after I do that 3 plus 3, whatever the side length is, I end up adding twice. So for this last one, if my side length is L, that means I'm going to add L twice. I'm going to do that cursive L the way they've got it in the table. I'm going to add that L twice. And by doing that, I find our perimeter. Now, I want to talk about this 3 plus L a little bit more because that's the way I was doing my math. I was using addition each time, but there's some other different ways people sometimes think of perimeter. Instead of saying 3 plus 3 every single time, you may have noticed, well, instead of me having to write 3 plus 3 each time, let me just put down a 6 because 3 plus 3 is 6. You are more than welcome to do that and then have plus L plus L. That is another option for how we could describe this function. Or you might have noticed instead of using addition each time, there's a way to write this with multiplication. So instead of that 3 plus 3, you might have said, I'm multiplying 3 2 times, and I'm multiplying that other side 2 times. So for example, with the 6.3s, you might have said, I'm doing 6.3 times 2, and written those as 2 multiplication problems. You could also do that. So down here, when it comes to the 6 plus 2L, you might have said 2 times our 3 plus 2 times that side length, like that. So you could have written that. Or you could have done that multiplication with the 6. So 2 times 3 is 6 plus 2L. That is also an option. There are many ways you could end up writing that perimeter. What they're all going to have in common is they all should give you the same perimeter up here. So if you're using that addition or you're using that multiplication, we should be getting all the same final answers. All of these are what we call equivalent. They all represent the same thing. what we want is, no matter how you represent this, we want something using that variable L so that we can use function notation to describe this function here. Remember, that is the goal of this last part. We're told we're going to call this function P and then use function notation to describe this. So the last part of this, putting it all together with what we know now about function notation, my function's name is P, so I'm going to start P of. After that is my input. My input is the variable L. So P of L equals, and then any of these here, whichever way you were thinking of it. I'm going to write that original one we had with addition, but any of these would be good. So we could say P of L equals 3 plus 3 plus L plus L. That right there is using function notation to describe how we find perimeter in this situation. There's one last part here for you. I'm going to have you go ahead and finish up this problem. So try numbers 2 and 3. Number 3, obviously, you can't sketch a graph on my screen, but you can do your own like little quick sketch of what this might look like. Does it curve up like the other line, or would it be a linear equation, be a straight line? See if you can figure that out on your own. Go ahead, pause the video and try numbers 2 and 3, and then come back once you're ready. All right, so for number 2, it's talking about P of 11. P of 11 is going to represent the perimeter of the paper when the side length is 11 feet. And that value of P of 11, we did that math earlier, it's up here in our table, is 28. So that means the perimeter is 28 feet. That is the answer for number 2. For number 3, this does end up being a linear equation. When you go to sketch your graph here, the y-intercept is going to start at 6, just because there was always that 6 that we were adding at the beginning. And then when we plot a couple more of these points, for example, side length of 1 we found is at 8, and then side length of 2 is at 10. And then if we do a couple other, 6.3 was at 18.6. That's not the most easiest thing to graph, but you could always definitely find some other easier points to plot. So for example, 3 I know is at 12. So you could pick some of those easier ones to plot, and you do end up getting a straight line. Now the question, can I draw a straight line? Oh, that wasn't too bad. Okay. So you do get a straight line, meaning this is an example of a linear function. But we can get those from using these pairs of numbers we already had in our table, or evaluating a couple more side lengths to figure out where those points should be on our graph. Again, we said this is a 2-part lesson, so part 2 tomorrow is going to be exploring these graphs further and how they relate to what we're talking about in this unit on functions. This is the last thing I've got for you all. I hope you all found this video helpful on how we can use function notation to help us start describing these rules and representing these situations, because that is going to be a big goal for this unit on functions. Thanks so much for watching. Bye.